Hello, Physics Nation. My name is Nate Larmond, and I'd like to describe the methodology of the pulley, the elevator counterbalance, or Atwood's machine. We're basically examining Newton's second law. So what did Newton figure out around 300 years ago? He figured out the relationship between mass, how much stuff is there, forces, push and pulls, and motion, specifically the rate of change of motion, acceleration. So that's what we're going to try to do. We're going to try to generate some experimental evidence that either confirms or denies Newton's second law. Don't get lost in the mathematical details. The penny on this side is a small force compared to the nickel on this side. So we got a little tug of war going on here. The nickel is pulling this thing counterclockwise. That is a positive Z rotation. That's coming at you. The penny, however, is rotating this thing clockwise. So that's a negative Z rotation. That's moving away from you. We have opposing torques, and so we actually take the difference of the two weights. That is a constant. We're actually not going to mess with the net force that's acting on the system. We're going to change the mass, and we're going to see how the acceleration is affected. So you can see my little ruler here. This falls about 9 inches. It's about 23 centimeters, or a quarter of a meter. Time is a little bit more tricky. This is the old school way of measuring time. You can use a pendulum. So, I'm no musician, but if you go 3, 2, 1, bang, bang, you're trying to get that time, 3, 2, 1, start, stop, the same as half of this period. Ready? 3, 2, 1, start, stop. Is it close? I don't know. 3, 2, 1, start, stop. Maybe. Or you can actually just use a stopwatch. I'll get into the mathematical details maybe in the next video, but all you're going to do is add the same mass to both sides. That way the force, the net force, remains the same, but the mass of the system changes. So we're looking for the functional relationship in between mass and acceleration. All right, so let's add a quarter to the penny side and another quarter to the nickel side. And like I said, the force imbalance remains the same. It's still heavier on this side, but now it's a quarter and a nickel. And it's still lighter on this side, but it's a quarter and a penny. So what's going to happen to the motion? Greater acceleration? Smaller acceleration? I don't know. 3, 2, 1, start, stop. You got that rhythm? Whoops. 3, 2, 1, start, stop. Now we try to tune the pendulum. Is longer, shorter? Well, I think it took a little bit longer, so we're going to make the pendulum a little bit longer. You ready? 3, 2, 1, start, stop. 3, 2, 1, start, stop. Maybe a little bit longer still. 3, 2, 1, start, stop. Okay? Finally, well, you can do as many trials as you want, but I'm going to add a second quarter to both sides. All right, so now we have 2 quarters and a penny on the light side and 2 quarters and a nickel on the heavy side. What's going to happen to the motion here? Again, the force imbalance, that is the net force, remains the same. But the mass of the system just increased a lot. So you ready? 3, 2, 1, start, stop. 3, 2, 1, start, stop. Now how long does our pendulum have to be? 3, 2, 1, start, stop. It's still a little too short. 3, 2, 1, start, stop. Anyway, happy experimenting. Design a data table, draw your graphs. Let's look for mathematical patterns in experimental data. Thanks for watching. See you in the next video.